Hello viewers, in this lecture we will see the transforming differential changes between two coordinate frames. So in the last lecture we have seen about the differential transformation. So to recall that one, if you consider a fixed coordinate frame f and another coordinate frame m, then if you write the frame m with respect to frame f, that is ftm, as the homogeneous transformation T, the position and orientation of m frame with respect to f frame is given by the 4 by 4 homogeneous transformation matrix T. And if we give a small translation and rotation with respect to the fixed frame, then the new position of T will become T plus del T. And we have written that in the last lecture we have seen that del T, the increment in the position and orientation of T is given by the differential operator into T, where this D is given by the rotation and small translation and small rotations. So, the differential operator D is given by the matrix 4 by 4 matrix, where dx, dy, dz represent the small translational components along the x, y, z direction of the f frame, and del x, del y, del z are the small rotational component of about the x, y, z axis of the f frame. So, the same thing can also be written as T times d superfix T, where this d superfix T is given by 0 minus del z superfix T. So, everywhere we will put a T along with the translation and rotation. So, these are the linear and angular small translation and rotational movement with respect to the m frame itself. For example, dxt, it means the small amount dx travelled by the m frame along the x axis of the m frame itself. So, similarly all the translation and rotation. So, these two are the differential. D means the differential changes with respect to the fixed frame, dt means the differential changes with respect to the current frame. Now, we want to relate these two. What are the relation between because this del t operator is equal to dt on one hand and t into dt on the other hand. So, the relation between d and dt can be easily obtained from this relation. So, the practical meaning of this will be very useful in the many robotics problems, etc. So, here d into t is same as t into d superfix t, as seen in the earlier slide. So, d superfix t is given by this formula, that t inverse dt. So, if you are able to evaluate this expression in the right hand side expression, we get the relation between d and dt, and then we can make use of them in certain problems. So, we denote this FTM, the M frame with respect to F frame, by the 4 by 4 matrix like this, where the first column represent the n vector O A P, some standard notation for the 4 columns of the homogeneous transformation. So, now if d is given by the expression here, t is given by this, and if you multiply d into t directly, we can easily see that the first row into the first column, the product will give minus del z into ny plus del y into nz. Similarly, the first row, second column, etc., directly can be multiplied, and we can see that this minus del y into ny plus del y into nz. So, that is the first element of this product, and that can be easily seen to be the x component of del cross n. This del cross n, it is given by del x I j k, del x, del y, del z, n x, n y, n z. So, this determinant, if you calculate, the ith component is del y n z minus n y del z. So, that is what we have seen here, this one. So, this is the first component, del cross n x. Similarly, all the components are given here, the product of for example, the first row, fourth column. The first row multiplied by fourth column will give this del cross p vector, and the last entry is dx into 1. So, that is given by this one, del cross p plus d vector, where this del vector we are calling it as del x I plus del y j plus del z k, and d vector it is dx I dy j plus dz k vector. So, the z x component of d is given here. So, similarly, all the entries can be multiplied, d into t can be obtained. Now, we have to multiply in the left side t inverse. So, T inverse dt can be obtained like this. It is because the T inverse, if T is given by the rotation matrix, the 3 and then P vector 0 0 0 1, where R contains the first row is, first column is N O A, and then this is P as shown earlier. So, the T inverse, if you recall, it is nothing but R transpose, the 3 by 3 matrix, and minus R transpose into P vector, then 0 0 0 1. So, if we multiply T inverse with this dt, d into t, so we can see that T inverse dt, the first row into the first column will give del cross n is the vector in the first column here, the dt, and the first row of T inverse, first row of T inverse is nothing but the first column of R, that is n x n y n z. So, if I multiply n x n y n z with this del cross n vector, it is nothing but the first entry will be n dot del cross n only, isn't it? The first column here is del cross n vector, the first row of T inverse is n vector. So, the product will give you n dot del cross n. So, similarly all the other components, the first row second element is given by n dot del cross O, and the third is n dot del cross A, etc. Just by observing the dt itself we can easily find. So, it is very easy to verify T inverse dt is given by this expression. Now, if you observe the entries inside the matrix, it is n dot del cross n. So, we know that if there are 3 vectors f, g, h, then if f is or any one of them is repeated 2 times in the this product, the triple product it is called, then it is 0. The value of the it is, for example, f dot f cross h equal to 0. So, wherever this is repeated, n dot del cross n is 0, and then O cross del cross O is 0, and A dot del cross A, that these 3 will be 0. Here n dot del cross P can be written as del dot P cross n and plus n dot d as it is here. So, we can write from each entry the values can be obtained as given here. So, the d superfix t is given by this expression. Now, again observing these vectors are unit vectors, n, o, a are unit vectors, and they dot products are 0, they are orthogonal to each other. That is the property of the homogeneous transformation. So, we can easily see that n cross O, these are mutually perpendicular vectors. So, we can get that n cross O will be the A vector, and O cross A will be n vector, and A cross n will be O vector. So, this can be utilized for this expression, and then substituting n cross O equal to A here, it is del minus del dot A vector, and this is del dot A cross n is O vector. So, this is del dot O. So, what we ultimately obtain is the D superfix T is given by this matrix 0 minus del dot A, del dot O, del dot P cross n plus D dot n, etc. So, it is a very straightforward simple formula which is relating D superfix T and the D matrix. So, ultimately if you observe here D superfix T, the notation for that is given by this one. This position represent the z rotation with respect to the current frame. This position represent the y rotation with respect to the current frame, and this is the negative of x rotation with respect to the current frame, etc. These are the translation with respect to the current frame. So, if you compare the corresponding values here, we can easily see that the angular velocity about the z axis of the current frame is given by del dot A, okay, where del is the rotational velocity with respect to the fixed frame and A is the vector in the T matrix. So, if you take the dot product between the two, that will give the angular velocity about the z axis of the current frame T, that is given by this one. Similarly, we compare for example dx t, the linear velocity along the x direction of the current frame is given by this one. It is del dot p cross n plus d dot n. So, we can directly compare this thing and then we obtain the following formula. This gives the formula that these are the linear velocities and then these are the angular velocity. So, what is important in this formula is, if we know del and d, if it is given, that means the translational velocity and rotational velocity with respect to the fixed frame, if it is given, then we can find the translational velocity and rotational velocity with respect to the current frame. Given the small changes with respect to the fixed frame, we can find the corresponding small changes with respect to the current frame. So, that is the important of this result. And here again we can make use of the form of this one. We can write del dot p cross n as n dot del cross p. This can be changed. This also can be written as O dot del cross p, etc. And then we can take this n as a common factor. We can get the result like this. Del cross p plus d is a vector which we can calculate, and then if you take the dot product with n, that is the linear velocity along the x direction, dot product with O will give the linear velocity along the y direction of the current frame, etc. So, now if we summarize this in a matrix form, we get here dx, dy, dz, or this is with respect to the fixed frame, and we can find it with respect to the current frame. So, this formula is a useful one too, which is relating. So, it is the transforming the differential changes between coordinate frames, f frame and m frame, we are transforming it, and this formula is useful in that context. So, for example, if at a particular instant, this is a given frame, and then in that frame you have the origin is shifted to 10, 5 and 0 somewhere here, and then the coordinate frame, new coordinate frame is the x axis of the m frame is 0, 1, 0, that is this is 1, 0, 0, 0, 1, 0, 0, 0, 1. For example, these are the I, j, k is the original frame, f frame, and the new frame which we are considering it as f, t, m, it is its x coordinate is 0, 1, 0 along this direction, and y coordinate is 0, 0, 1, it is along parallel to the z axis, and then 1, 0, 0, this is the. So, we have here x here, y here, z for the new coordinate frame. For this it is x, y, z. Now, in this frame, if you are giving a small translational velocity along the x and z direction of the fixed frame, that is 1 unit along the x direction, x axis of the fixed frame, 0.5 unit along the z axis of the fixed frame. If you are shifting it, and then we are also rotating 0.1 radians about the j axis of the fixed frame, that is we are rotating it like this. So, this will obtain a new position somewhere else. Okay, we will get a new coordinate frame after making this much of change with respect to the fixed frame. Now, the same change, the new position, by giving small changes with respect to current frame itself can also be obtained. So, how much of translation rotation should be given with respect to the current frame for obtaining the same effect. So, that is calculated by this formula as given here. So, here n matrix is the first column is 0, 1, 0. So, it is j, and the O second column is k vector, and third column is I vector, and the fourth origin is shifted to 10 I plus 5 j position. So, and the del cross P is calculated, where del is given by this one, this vector, and D is given by this. So, del cross P can be calculated. Del cross P plus D is finally this one, this transformation, and then by using that formula, this formula, we get the rotation with respect to the current frame is n dot del O dot L etc. can be calculated again using this expression. This formula is between two coordinate frames. If you have F frame and M frame and the differential changes, but if you have a chain of transformations in between, then how to do it, that we will see now. So, let us consider a fixed frame, and there are several other frames, let us say, etc., and then finally we get a frame like this. So, let us call it as, instead of fixed frame, we call it as the 0th frame, and this is the first one, this is second, and then this is nth frame. Now, the relation between the starting frame, that is 0th frame, and the nth frame, we can write it as 0 T n, and the relation between 0th frame and the first frame is 0 T 1, the homogeneous transformation between 0 and 1 frame, and then homogeneous transformation between 1 and 2 frame is given by 1 T 2, let us say, and then 2 T 3 etc. The last but one is n minus 1th frame, and then this is the nth frame. So, let us say there are n such chain of frames available, and the first and last frame is related by 0 T n by multiplying all these matrices. So, each one is a 4 by 4 homogeneous transformation, as we already know. Now, if there is a small change, if you are making changes at each and every frames, a small translation and small rotation is made in the 0th frame, that will affect the last frame also. If you make any change here, the last frame will also be affected. Similarly, if you make any small change in the first frame, again the last frame will be affected, etc. So, the small change at each and every frame will affect the last frame. So, we want to calculate, if you call it as the T matrix, T is 0 T n. So, what is the differential change dt, as we have calculated earlier? How to calculate the resultant changes that happened between all these frames, and then the result on the nth frame, that is given by d into t, as we have seen earlier. So, how to calculate that? That is, we have to add all such changes, because these are all partial changes. If you consider only one change in one of the frames, that is called the partially, we are considering a change that will affect the end frame. Now, if you add all such changes, all such partial changes, we will get the total change, the total differential change of t. So, finally, that is equal to dt, let us say. So, what is the D matrix which we have to calculate? So, that is given by the change with respect to the first frame, and then plus the change with respect to the second frame, etc. So, what we should do is the differential change that happened in the first frame, we call it as T1. So, instead of let us write 0 T1 as just T1 I am mentioning, and then 1 T2 I can mention as T2, etc. Tn. So, we are just considering the change that has happened in the first coordinate frame and multiply all this, plus now we consider the change that has happened in the second coordinate frame, that is 1 T2, that is T2 up to Tn. Because D2 will not affect the first frame anyway, whatever changes that are happening in the second frame, that is not going to affect the previous frame. If you change in the second frame, it will affect the third frame, fourth frame up to nth frame only, not the previous one. The third change is T1, T2 will not be affected, but the change in the T3, that will be up to Tn, etc. So, T1, T2, Tn minus 1, the last one is Dn minus 1, Dn, Tn. So, these are the total changes we have to calculate for this one. So, this we can substitute here. So, whatever changes we are making for the first frame, so this is given by 0 minus del z 1 we can call, and minus, that is del y dx dy dz 0 and del x So, this is with respect to the first frame. So, we can write here 1 along with all these entries. So, I can write 1 here into T1, T2, etc. Tn. So, similarly T1 multiplied by the similar matrix, but 2. It denotes that all the entries are different because the translation and rotation changes which we are making for the first frame may not be the same for the second frame, etc. So, even though the entries will look similar del z, etc., but this 2 indicates that these numbers are corresponding to the changes in the second frame. So, similarly up to n, d1, d2, dn, they are all different differential changes matrices that can be added here. So, if you add completely all of them, that will give the final total change in the end effector, the end frame, that is 0 t n frame. Whatever changes that has happened here will be obtained by adding all these terms. Finally, we will get a consolidated matrix that is given by the expression. This is the procedure for finding the total differential change of the frame T by adding all the partial changes with respect to each intermediate frames here. So, using this procedure, we will define the manipulator Jacobian in the next lecture. Thank you.